Welcome. Today we're going to talk about linear regression, one of the most fundamental tools in machine learning. Now, before we talk about linear regression, we're going to review some basic calculus, which you should already know, but just because it's the first time we're seeing it in this course, I'm going to review some of it. But I'm going to do it relatively quickly and just review some terminology, and I'm going to assume you know it from here on out. Okay, first of all, a derivative, which I'm going to pretty much assume you know, but let's just say what it is. So if we have a function f, let's say f of x, which maps from r to r, that is, it takes in just one value and it outputs one value. Then there's a function known as the derivative, which can be written as f prime of x, or equivalently is equal to df by dx. And this is going to be a function, again, which maps from r to r. That is, it's just going to be a function which takes in a value and computes the derivative specifically at that point. So, but it can be more broadly viewed as a function, even though it's often evaluated just one point. So just as a simple example, which should hopefully be very familiar to all of you, consider the function f of x equals x squared. X squared. Well, we all know that the derivative of this is going to be f prime of x is equal to 2x. So there's another function which we can in particular evaluate at any particular point we want to know the derivative at. Good. So this is quite standard. Now, a gradient is essentially the higher dimensional analog of a derivative for when you have a function which takes in a vector instead of just a scalar. So just to make it a bit different, and because we often use it with w, I'm just going to write, I'm going to use f again, but let's say f of w. This is a function which takes in, suppose we have of fw, which takes in a d-dimensional vector and maps to just a scalar value. Well, in this case, we use this funny symbol here called, I don't know, nabla maybe it was called, but the point is we take the gradient of a function, which is equal, well, let's say this is a function. Now this is a function which takes in a d-dimensional vector, and it maps not just to a single item, but it's going to be a map to a vector. And so yeah, it's basically, what is the gradient? Well, it's going to be essentially the vector, which consists of the partial derivative of the function with respect to each of the variables. So d of f, partial of f with respect to w1, all the way through to partial of f with respect to wd. Yeah, so there's going to be d entries here, and you can see each of them is just going to be a function which takes in one value and outputs one value. So yeah, this is the gradient. This is one of the most basic objects in machine learning, so you should learn it and be comfortable with it. Now, the last object I'm going to mention is what's known as the Hessian of a function of a vector, a function which takes in a vector and outputs a scalar. So just like how we have second derivatives, so the second derivative of a function f, say double prime is equal to, say, 2 here, that just like we have second derivatives, well, the kind of equivalent of this would be what's known as the Hessian matrix. So let's write what that is. It's going to be something like this. So the Hessian, which is written like this, is going to be a function which maps now from Rd, and the output is going to be a matrix to the size Rd by d. And what is the shape of this? This is going to be basically the matrix of second derivatives. So let's just write it like this. It's going to be something like this, and essentially the first element is going to be the partial of f, or the second partial with respect to partial w1. I guess, yeah, I'll just write it like this because it's more consistent. And in general, it's going to be elements like this where the ijth entry, this is say entry I, row I, column J, here we have the second derivative of f with respect to wi and with respect to wj, and so on. We just fill in this entire matrix as this. It's just the matrix of second derivatives. So, okay, that's essentially all the terminology we need to know. The idea is these can broadly be viewed as some sort of function, but if you evaluate them at a specific point, which we will often do, then it's just going to be a matrix or a vector respectively. And gradients are really everywhere. You're going to see them all the time, so definitely understand this very well. Hessians are a little bit less studied, so don't worry about them as much, but gradients definitely know like the back of your hand. Cool. Okay, so with this terminology out of the way, let's get to linear regression. Yeah, so in the previous lecture, we talked a little bit about a broad setting of like how to sort of phrase binary classification in a sort of general way, what our goal is. But let's make this even more general, where we want to do generally some sort of statistical learning. So let me write it like this. We have some sort of data set, which is x1, y1, all the way through xn, yn. And this time, again, we know, say, that the x's are in r to the d. And before we assumed that the yi's were 0 or 1, but now let's think of a more general setting where, say, the yi's are going to be in, say, r. They're going to be just numbers as well. We could even consider more general settings where they're also d-dimensional or some other dimensional, d-prime dimensional vectors, but for today, we're just going to focus on something like this, where we're just looking at general numbers. So it's not necessarily going to be just a classification task this time. When we're doing a regression task, this generally means that we want to predict some, say, continuous value in general, broadly speaking. Okay, so now if we have this, then what we need is some sort of loss function. And yeah, a loss function, which essentially we're going to define in terms of a specific point x, y, and it's going to have some sort of, it's going to be parameterized by some parameter w. And the idea is this is going to be the loss function. Why did I write this twice, actually? And I'm going to keep this a bit abstract, but we're going to make it a little bit more concrete in a second. So this is the loss function, which says essentially, suppose this is the input. Sorry, let me say it like this. Suppose that x is some sort of the feature vector that you're given, and you apply some sort of parameters w. Then how good is your prediction compared to the actual label y? So essentially, this is what we're going to be What we're going to be doing is trying to minimize this over. Sorry, let me just write this, and then that'll be clear. The goal is to find some sort of vector which can minimize this. Where we imagine a point x, y is drawn from the same distribution as a training set. So this is our goal, that we're trying to optimize this. And we're given x1, xi, yi, which are drawn according to some distribution d. Good. So this is the setting. Let's compare this to what we were looking at in the previous lecture. In the previous lecture, our loss function was in fact very simple, where our loss function was essentially basically a prediction task, where our loss function of wxy, this was equal to, what was it? It was equal to 0 if sine of, say, the inner product of w and x is equal to y, and 1 otherwise. So essentially, this was the loss function that we were implicitly using in the previous lecture, where we are going to get it right and not suffer any loss if we predicted the sign correctly with the perceptron. And otherwise, if we predicted it wrong, then we suffer loss 1. And so you can see, as we wrote exactly in the previous lecture, the expectation of this is that we're minimizing the equivalent way of writing this with this loss function. This leads to the objective function that we're trying to minimize, which is argmin over w, the probability that sign of inner product of w and x does not equal y. This is essentially exactly what we wrote in the last lecture, pretty much, where x, y are drawn from the same distribution as the training data. So now we're just basically looking at the same type of thing, except in a somewhat more general setting. Now, how do you solve these? In general, the way that we can solve these is by something this is often solved using something known as empirical risk minimization. And what does that mean? Well, it means the following. We don't necessarily know what this distribution D is, so we have to look at the data, which is drawn from the same distribution. So the idea is that if we try to minimize this function over the data, then maybe it'll generalize pretty well. So in other words, our goal in empirical risk minimization, write that, or this is often called ERM for short. What we do is, since our goal is to minimize this, what we instead do is we look at the data that we have, which is, and we try to optimize it over that. So we're trying to do arg min over w, 1 over n summation of the loss xi, yi. So yeah, this is what we try to minimize. We sum over the data set and we try to find a loss function which minimizes the average, we try to find a parameter vector which might minimize the average loss over the points in our training data set. And if you're familiar with the law of large numbers, then informally this converges as we have n to be large enough. This converges to arg min over w of expectation lw xy, where xy is drawn from D. And this is exactly what our goal was. So essentially in the infinite limit, then this will work. And so that's a pretty good bet for trying to do to solve this problem. So yeah, this is kind of the most common thing that we do. We define some sort of loss function that we're trying to optimize over new training data set or new test set samples. But in order to optimize that, what we do is we pretend we just try to solve the same problem except on the training data set. And that's what's known as empirical risk minimization. Good. So let me comment on what we're trying to, how do we choose this loss function? Well, there's a lot of thought which goes into choosing the right loss function, and it matters based on a number of different things. For example, what type of things do we believe upon our data generating process? For example, when we were doing perceptron, we kind of made pretty strong assumptions on what the data generating process looks like. The idea that there exists some sort of hyperplane where things that lie on one side are going to be positively labeled and things on the other side are going to be negatively labeled, which was maybe a strong assumption. And yeah, whenever we're doing any sort of problem, we're going to have some sort of assumption when we're choosing our loss function. But no matter what we're doing, there's one very convenient feature of our loss function, which makes a lot of our life a lot simpler. In particular, one thing that's going to be very useful is the property of convexity. So convexity, I think this should be familiar to all of you, but we're just going to talk about, we'll talk about some properties of convexity and what it means and stuff like that. Now, when you hear people talk about convexity, there's always one picture that is drawn, and it's something that looks like this. So this is a convex function, and it's a caricature of one, but it's something which looks kind of like a bowl. But this is not quite precise. This is not a good way to define what a convex function is, so I'll try to define it a little bit more precisely, and then I'll actually give you a mathematical definition. like one of the nice properties that we have is the following, where if you connect 2 points on the line in a convex function, well, then the any point on this line is going to be above the function. That's essentially all it's saying. So let me define a few of these points, or like name some of these points. So we can write this as, let's say this is x1, x2, and we can write this point in between them as a linear combination of those 2 points. And so we typically do this as lambda x1 plus 1 minus lambda x2 for some lambda in 0, 1. So you can see we can compare how this point here looks like this point here. So essentially what convexity says, or what a function being convex is, we say function f. I drew this picture in 1D, but like I said, it could hold for multiple dimensions. So we'll write it like that. So f is convex if and only if this inequality holds. So this is called Jensen's inequality. So the way we write this is the function here, so that point is lambda x1 plus 1 minus lambda x2, is less than or equal to this point right here, and this is the line connecting them. And this line connecting the two can be written more conveniently as, or let me, the line connecting them can be written conveniently as just a linear combination of those 2 points. So it just becomes lambda f of x1 plus 1 minus lambda f of x2. So this is known as Jensen's inequality, and it holds if and only if a function is convex. And yeah, this is very convenient. And what does this mean in terms of optimization? When we're in the optimization world, this is kind of nice because the idea is that when you minimize a convex function, then this is the, and then any local minimum is a global minimum. So this is what a convex function looks like, but let's take a look at what a non-convex function might look like. So this is convex. Oh, before we continue, let me just mention that another equivalent characterization of a convex function is the following. It can also be said it's convex if and only if we have the following thing for a one-dimensional function. This is probably more familiar to you. But if the second derivative is greater than or equal to 0, so this is for 1D functions. And for higher dimensional functions, let's say something of d when d is greater than 1, then it's something a little bit less familiar perhaps to some of you. But what you need to say is that the second derivative matrix, that is the Hessian of f, I'll just say that for all x, this is for all points in the domain, we have this, that we need the Hessian matrix to be what's known as positive semi-definite. So you can see I draw this funny greater than or equal sign here. And so this is it says that the Hessian has to be positive semi-definite. So now what does it mean if a matrix is positive semi-definite? Well, it's essentially the same type of thing as a function being non-negative, but it's for matrices. So remember, this is a matrix, which is d by d. So what do we, let's define positive semi-definiteness. So a matrix M in, say, R to the d by d is PSD. Let me just write it out fully, positive semi-definite. And we just say PSD for short. If and only if that we have a matrix, let me write this as, the matrix has the following property, that V transpose MV is greater than or equal to 0 for all V in RD. So yeah, these are two kind of equivalent ways. So let me just say, yeah, that this is essentially the way you say a matrix is non-negative. Where a function is being non-negative, it's very sort of easy to see. You just plug in something and see if it's non-negative. But a matrix being non-negative is something more like this PSD constraint. And these are both equivalent ways to say a function is convex. Cool. So we'll revisit this a bit later to see why it's when this can be useful for seeing whether a function is convex or not. But yeah, convex functions are very nice for optimization because they look like this, vaguely speaking. Let me show you what a non-convex function might look like. So a non-convex function could look something like the following, where we have, say, something which goes down and then maybe up like this, and then have something that goes further down over here, so on. This is a caricature of what a non-convex function is. But the nice thing about this is a convex function is the fact that this point right here, this is both the global minimizer of the function, and it's the only local minimizer. Whereas here, you can see that at this point we have a local min. That is, if you go left or right, you can't get any smaller, but this is not necessarily equivalent to the global min. And then there's other points which might be kind of misleading as well when you're doing gradient-based optimization, which we'll talk about in a sec what I mean by that. But for example, this point here is sort of it could be a local max or a saddle point. Let me just write it as a saddle point. But roughly speaking, we'll formalize this in just a sec, but the thing that's nice about convex functions is that the only place where the derivative is equal to 0, where the function is sort of horizontal, is going to be the global min, whereas in a non-convex function, there's potentially many points where the derivative could be equal to 0, not necessarily just the global min, but also local minimum and saddle points, any sort of extrema of the function. So that's something we have to worry about. And a little bit more mathematically, let's I'll write it on the next page, I guess. So the key sort of point here is something known as Fermat's condition. And this says if f is let's say an extremum, a local extremum, then we have of f, then we have the fact that the derivative or the gradient there is going to be equal to 0. So let's just say we're in the more general setting where we have a multivariate function. Sorry, I didn't write this right. Let me change this to if x is a local extremum of f, then the gradient of f at x is equal to 0. So essentially this says that in something like this picture, any of these three extremums here, then we have that the gradient is equal to 0. However, like we sort of saw in this picture, the opposite is not necessarily true. But like furthermore, if f is convex, then it goes both ways. And by that we mean that if the function is convex, then the gradient being equal to 0 means that we have the only local extremum, in fact, the global extremum. So let's just write that gradient of f of x equals 0 implies global extremum. Good. So that's, in short, we went a bit into what convexity is here, but the reason that it is convenient for when we're doing optimization is because of the fact that if it's convex, then we can just simply find a point where the gradient is equal to 0, and that will give us the globally optimum solution, which is great because it says we properly optimize this model as well as we possibly can. yeah, a big problem in a lot of machine learning in general is trying to optimize a function, because maybe you'll get stuck in a local optima. If you're stuck here, then maybe you can reduce the function a lot more, but just you don't know how to get out of this. Good. So that's, I think, everything I want to say for now, just broadly speaking. But let's talk about, let's try to apply what we've learned so far in the context of linear regression, the concrete, which is an actually concrete problem. Okay, so linear regression, what is it? Well, linear regression looks something like the following. Let me just give you an example. So linear regression can be seen as something like this. So imagine we have a simple thing here where on the x-axis, perhaps what we're going to do is we essentially want to understand how people tip. So on a purchase. So imagine here on the x-axis, you can have someone's bill, and on the y-axis, you have their tip. So maybe, I don't know, someone's bill is something like $10, and they tipped maybe, I don't know, $2, like this, right here. And then maybe someone else, they paid, their bill was $20, and they tipped, say, $3.60 or something. And so maybe you have a bunch of people like this who have different bills and different tipping amounts, and it looks something like this. Yeah, maybe something like this. And the question is, what is the best way? You want to essentially have a predictor saying that if you're given someone's bill, can you predict how much their tip is? And just by glancing at this, you might have already sort of filled in the blanks in terms of thinking, okay, so if we want to get a predictor, then maybe we just draw a line that looks something like this. Informally, that's kind of what linear regression does. Well, yeah, that is generally what linear regression does, but we have to be a bit more precise as to what exactly we're trying to do here, what the loss function is, what we're trying to optimize, and stuff like that. So when we're doing linear regression, the typical way we do it is least squares regression, meaning remember how we did this back here. We sort of have to define some sort of loss function. Well, what we're going to do is define our loss function to be as follows. Our loss function is what's known as the squared loss, or the squared error. So let's write that. LW x comma y. This is going to be equal to the following. It's going to be equal to y minus the inner product of w and x, and you square it. That's it. So let's comment a bit on this loss function. First of all, one thing that's nice about this is a convex loss function. We're going to prove that in a little bit, not yet. We'll do this a little bit later. Now, how can you picture this? What is it trying to optimize? Well, it's essentially going to try to find a line which minimizes the sum of these residuals. So what is a residual? It's basically the distance between this trend line and the points. So basically you take this value, and then this is some difference y, like I'm not going to write it here down, but essentially you take this distance and you square it. Let's say this distance is, say, I don't know, there's probably some symbol that people typically use for this, but let me write it as like gamma. So this is gamma 1, this here is gamma 2, and then this distance here is gamma 3, gamma 4. But essentially, the loss function, the total loss that we experience due to picking this trend line, is going to be the overall loss is going to be equal to sum of the residuals squared. And that's essentially just rewriting what we had here for one point and summing it over all the training points. So that's how you can visualize what linear regression tries to do, minimize the sum of squared errors. Now, there's a few more things to comment on. So one thing, as we wrote it here, this is just going to be a function which goes through the origin. But remember that we have this padding trick that we used before, where we can also, one could also consider a version where you have this, say, also with some b term. But we're not generally going to do that, because we're just going to imagine that we have, remember, padding, that we have x comma 1, and then here and w is augmented by sticking in the b parameter. So we have like kind of w comma b. So this is kind of like the padding trick where we just augment them each by adding one more dimension, and then we can just sort of hide the extra parameter in here without having to worry about it. So that's just the padding trick that we saw last lecture. The other thing is the fact that as described here, we have that y is just a number. So y is in R in this example. We could also have y to be in RT, and then we'd have basically be trying to predict a t-dimensional vector instead of just a 1D value, a scalar for each point. So this would be a multi-dimensional picture, which is much harder to visualize. And then you can similarly do a lot of the same derivations, but I think it just unnecessarily complicates things. So I'm not going to get into it during today's lectures, but you can check out the notes if you care and the recommended readings. Yeah, it's essentially going to be a bit more complicated because now you can no longer take just the squared this value. So you'd have to take the L2 norm and then, yeah. Okay, so this is least squares regression, least squares linear regression. There's now, since we have linear regression, you might also think that could you have more complicated regressions? Like for example, there's also polynomial regressions. For example, if you had a data set that looks something like yeah, the data set which looks something like this, then in fact maybe, you know, a degree 3 polynomial might be the right thing to fit here. Something like this seems like the right sort of thing to predict instead of just a line, because a line wouldn't do very well. But yeah, so this is just a very special, the simplest case, which is often pretty good for, yeah, it's often good for many cases. But if not, then we have something called kernels, which we'll talk about in a few lectures from now, which kind of captures polynomial regression. Okay, so this is linear regression, and this is the problem. Now let's study some things about this linear regression. First of all, the first thing we're going to want to show, or first thing we're going to want to understand is whenever we have a loss function, it's nice to understand some properties of its loss function. In particular, what does the gradient look like? And also, what does the Hessian look like, which is useful if we want to show that as a convex function. So the first thing we're going to do is we're going to derive both of those. Then we're going to see that the Hessian is going to be a positive semi-definite matrix, and that will prove that this is a convex loss function. And finally, we're going to see how the gradient of this is nice, because since the gradient is so nice that it'll allow us to, in fact, derive a closed form expression for the optimizer for this function. Remember, because we're trying to minimize this over our training set. Now, there's other cases, most other cases we won't have such a nice property, but yeah, here we will, which will make it really nice. But in future lectures, we'll see how we'll have to optimize things via gradient descent. Cool. All right, then. So like I said, let's start by first we're going to rewrite this loss a little bit. So the way we'll rewrite it is first we're going to want to, instead of writing the loss as the following, so we start with the loss, which is summation of maybe 1 over n, but I'll leave out the 1 over n because we're just trying to minimize it. So a constant multiplicative factor in front doesn't really matter much. So what we're trying to optimize is yi minus wxi squared. And let's rewrite, let's use a few shorthand notations. So we're going to let A be a matrix, which is the following. Each row is essentially going to be one of our data points. So the x1 is going to be the first row, all the way down to xn being the nth row. That's one thing we're going to do. And just so that we're on the same page, this is going to be a matrix with n rows and d columns. And we're also going to define a vector, z, which is equal to, just stack the results in a vector like the y's, y1 all the way through yn, which is of course a vector of size r to the n. And in fact, an equivalent way to write this loss function here is going to be the following. we just write a times w minus z L2 norm squared. And why is this? Well, let me try to illustrate why this is. Because consider just, okay, what this is going to do, this essentially what this L2 norm squared of this vector means is you're going to take the entries of the vector that comes out of this difference and square them and sum them. Well, let's just take a look at what a single entry of that would be, what a single entry of that vector would be. So let's just take a look at the first entry of this vector. Well, the first entry of that vector would be the inner product of A, of the first row of A. So the first entry of the vector would be the inner product of A1, I'll just write it as x1. And then remember, we're going to take the product with W. So it would be the inner product of x1 and W. That's just the first entry there. Then we subtract y1. And then we take the square of this value, because again, it's the L2 norm squared. So you can see that the first entry of this vector is just going to be the loss on the first point. And since it's the L2 norm squared, then we just sum it over all the different points in the data set, and it'll give us exactly the same loss function we had before. So this is just a more convenient way of writing this, this loss function. And why is it more convenient? Well, let's try to expand it and see what happens. So when we write this as, we can write this out as follows, just by noticing that it's a square. So the way to write a vector squared, another alternative way of writing it is AW minus Z transpose times AW minus Z. And we can expand this out. Well, first of all, let's write the first thing as follows. W transpose A transpose minus Z transpose times AW minus Z. And expanding out this this product, we can see this gives us W transpose A transpose AW. Something like this. And some of these terms can be grouped. So we can write this also as W transpose, A transpose, AW. And note that these two things are both just scalars. So they can be written by just grouping them together. So this would just, it's the same value whether or not you transpose it. So yeah, let me just say that this is equal to 2 Z transpose AW plus Z transpose Z. All right, so now our loss function for the overall, the sum of the individual losses is going to be the following. And this is just an equivalent way of writing our loss function. Now, what we want to do is we want to take the gradient of this, and this might seem intimidating at first. How do we take the gradient of this? Well, I'm just going to make a claim as to, let me state a useful lemma. It's the following. I'll prove this in another video, which I'll upload as well, but I just don't want to throw off the flow of this too much. So let me just say, if we have some function f on some x, which is equal to x transpose ax plus x transpose b plus c, then the gradient of f at x is going to equal a plus a transpose x plus b. So this essentially gives us an easy way to write out the gradient of any sort of quadratic function. Now, like I said, I'm not going to prove it now, but check out one of the other videos I'm uploading which has the proof of this claim. But okay, so to continue with what we were doing, let's just essentially just plug this, take the gradient of this function and plug it in to this, we'll take the gradient of this function by plugging in the function to this claim. So that's not too hard to do. So then we have that the gradient of w minus z norm squared this is equal to, yeah, so just, okay, we have a variable clash, but it's not too bad to see that this can be written as, this A transpose A here is kind of the matrix A here. So we can write this as A transpose A plus A transpose A transpose times W, so the gradient with respect to W, and then we have minus 2, minus 2 times, let me write it like this because it's equivalent, A transpose Z. Yeah, because you could write it as, yeah, this will have the things match up in terms of dimension. Okay, so this is one way to write the gradient. Let me just sort of note that also these two are the same, because if you take transpose as a symmetric matrix, so this will just be 2 A transpose A W minus 2 A transpose Z. Now, what did we, let's, first of all, now that we have this Hessian, or sorry, we have the gradient, now let's compute the Hessian of this function, just because we want to verify the fact that this is a PSD matrix. Or sorry, to verify that this is a convex function by checking that the Hessian is positive semi-definite. So the second derivative of this, the Hessian matrix of A W minus Z, this actually we can just apply the same thing again. It's a much simpler case because we don't even have this sort of quadratic term, but I'll spare you the detail. You can check this yourself, but we'll find that the Hessian of this loss function is equal to 2 A transpose A. Now, my claim is that this matrix is positive semi-definite. And why is that? It might not be obvious at first. Well, let me just sort of explain it why. Well, a matrix is positive semi-definite, as we said, if, like, what condition do we want? We want that 2B transpose A transpose A V, we want this to be greater than or equal to 0 for all V. Well, this is true because of the fact that we can just write this as, if we group this, we note that this is basically just taking the inner product of a vector times itself. So this right here is equal to 2AV in L2 norm squared. And since this is an L2 norm squared, this is always going to be greater than or equal to 0. Therefore, we've shown that the Hessian, this matrix here, is going to be always, it's going to be positive semi-definite, and therefore this is convex. Like the loss function is convex. So great. This is convenient. I said that the loss function being convex is a very nice property that we'd want, because the fact, why was it? Let's scroll up a bit. Well, what we said is that if you can set the gradient of a loss function to be equal to 0 for a convex function, then we'll reach a global extremum. So that makes our life very easy now, because in other words, we can optimize linear regression simply by taking the gradient of the loss function and setting it equal to 0. Well, in this case, we just derived the gradient of the loss function, and we can find the point exactly at which it is equal to 0. So let's take this and set this equal to 0. What we do is we want grad W is equal to 0. And so this is kind of equivalent to A transpose AW minus 2A transpose Z is equal to 0. Well, rearranging that, this gives us A transpose AW is equal to A transpose Z. And now, note that we're trying to find the W which solves this. We're trying to find the W which sets this equal to 0. So in other words, we have a closed form expression for the optimal solution. So essentially what you want to do is solve for a W hat, which is equal to Okay, let me just write it like this, actually. So you can optimize least squares by finding W hat such that A transpose A W hat is equal to A transpose of Z. Now, you might just be thinking, maybe you've seen this before, that you can just take the inverse, W hat equals like A transpose A, and inverse A transpose Z. So can you do this? Well, sometimes. Sometimes you can do this if the matrix A transpose A is invertible. It won't always be invertible, but there always will be a solution to this type of least squares solution. But in general, it won't necessarily be invertible, so you can't always do this. And another reason you won't want to do this is because taking the inverse of a matrix is generally a kind of costly operation, in the sense that it might be computationally expensive in terms of a lot of operations, but also if you have an ill-conditioned matrix, say some numbers are very big in the matrix and some numbers are very small, then doing this inverse may be numerically unstable, meaning that you'll get some errors which are much bigger and give you a wrong error or wrong answer just due to numerical instabilities. So instead, what you can do is treat this as a linear system where, note that everything on the right-hand side, this is just going to be a vector where you know every entry, and this is going to be a matrix times a vector where this vector has n unknowns. So essentially it's going to be, d unknowns. So it's going to be a system of equations where there's d equations, d unknowns, and you can solve for any solution to the system of equations. So just using, say, Gaussian elimination or whatever you like to do to solve linear systems is a way to find a solution. Good. And so that's basically it for linear regression. What you do is, all you have to do is you have to set up this linear system like this and find a W which satisfies this equality. And once you do that, then you can do your prediction for any new point. So for example, like just to really hammer the point home, if you're given some new point X and you want to be able to predict what the Y is, well, then you output the prediction, which is Y hat is equal to W hat, the inner product of W hat and X. And that's your prediction. Good, so that's how you solve least squares. In the next part, we're going to talk a little bit more about how to justify the squared loss. Like, it was mathematically convenient, but why is this the right thing? Well, we'll talk a bit more about why it can be justified, and also some cases in which we'll maybe try to use a different type of loss functions for various reasons.